The agenda for today, well, a brief welcome. I will try to shut down myself because I am speaking too much. I will give the floor to our project coordinator, Judith Kessens, in a few minutes, and then we will go, as I was speaking before, through the Plast2bCleaned results. That presentation will be on behalf from Sebastian Reinhardt and Lucy Prince. We will have a short break of 5 minutes for you to take a coffee or maybe go to the toilet because this is quite a long session. And then we will continue with advanced sorting and impact assessment. And finally, we will have our panel discussion with Tom Carris, Roland Jossens, and Marco Garelli. So certainly you can address them your questions on the discussion that will be arising later. And if you haven't checked that before, we have a video, a nice video for the end of the session, so you can check it out later on. And from myself, nothing else to add. I will now give the floor to Judith. So she will be going through the Plast2bCleaned project. Thank you all very much. I really hope you enjoyed the session, and I will maybe come later with some questions for the panelists and speakers. Thank you very much. Judith, the floor is yours.
Yes. So thank you, Mariana. My name is Judith Kessens from TNO, and TNO's coordinator of this project. We are very pleased today to present more of the results of our project. And what's the motivation for Plast2bCleaned? Well, there's a global increase in the e-waste. It's a fast-growing waste stream. And currently, this waste stream is not yet sustainable, so there's much to be gained. Some waste is even incinerated, while there's a lot of value in it. One of the issues is that it contains legal additives, and in order to recycle it, it needs to be separated. And this needs to be done in an environmental and economical feasible manner. So that's the reason why we started this project, Plast2bCleaned. And Plast2bCleaned is an abbreviation for plastics to be cleaned by sorting and separation of plastics, and subsequent recycling of polymers, bromine flame retardants, and antimony trioxide. It's an EU-funded project, and it started at the 1st of June in 2019, and it will end next week. And in total, we got a funding of around 4.5 million euros. There's 10 partners collaborating, and TNO is coordinating. As has been said before, the overall aim of this project is to develop a human and environmentally safe recycling process for waste electrical and electronic equipment in a technical feasible and economical viable manner. And in this project, we developed key technologies, which are improved sorting of the WEEE plastics, dissolution of the plastics in superheated solvents, the separation of additives to concentrate the BFRs and the ATO fractions for recycling, and energy-efficient recovery of both the solvent and of the polymer. So here you see it also graphically. We do this by closing 3 loops. First of all, the polymer loops, the bromine loops, and the antimony trioxide loop. Next, we integrated all and we scaled it up. And finally, we performed the testing of both the products and the demo products made of the recycled materials. And during the whole project, we did system optimization, and we did assessment of both the sustainability and economic viability. And in order to make this process feasible, we also developed a new innovative method of pre-sorting the WEEE plastics. In this project, we collaborated with different partners, and these partners were chosen in such a way that we covered the complete plastic value chain. So first of all, we have recycling company Coolrec, and then we have industries, so the polymer industry, bromine industry, and antimony fraction industry. So Alex is a plastic producer, ICL for the bromine recovery, and Campine for the antimony recovery. And finally, we also included an end user of the recycled materials, and that's Electrolux. Then also various research institutes were involved in order to support the research needed in order to achieve it. And also we included an engineer company which helped in making all technical feasible. And last but not least, you already saw Mariana from Sustainable Innovation, and they are helping us with communication, dissemination, and exploitation. So what's the impact of this project? First of all, we try to achieve a recovery yield of 80% and an increased recycling rate of WEEE. And in this way, we hope to reduce CO2 emissions, and we are closing 3 loops. And at the end, we like that this process is profitable in an economic way. Well, and this is the team, all the people that make the results that you will see later on in this webinar possible. It was a nice team, and we had a lot of fun, but also we made nice results, which will be presented today. Then I also like to introduce the work package leads that were responsible for the main parts in this project. So for the advanced sorting, work package 1, it's Ainara Boschville from Geiker. Then for process development, we have Annemiek van der Runstraat from TNO. For scale up, we have Sebastian Reinhardt from ICT Fraunhofer. For the performance testing, Anna Rita was leading this work package, and she's from Coolrec. And then for the impact assessment, Toon van Harmelen from TNO was leading, and you already met Marianne Fernandez from Sustainable Innovation, and she's leading the dissemination and communication and exploitation work package. Then, with this short introduction, I like to give the floor to both Sebastian Reinhardt from Fraunhofer and Lucy Prince from TNO.
Thank you. In this presentation about the Plast2bCleaned process, we will jointly, together with Sebastian, walk you through the process from the lab scale and how we transfer it to scale up pilot. Yes. So first of all, I would like to start with a brief overview of recycling technologies. We have material recycling and chemical recycling. In material recycling, we can focus on mechanical recycling, which basically takes the waste stream, and the product is just a mix of the properties of material that comes in, and the final mix can be reused. The drawback is that often it leads to downcycling of the materials because only a limited amount of impurities can be removed. On the other hand, we can have a solvent-based recycling or purification, where a solvent is used as a medium to enter the polymer matrix, facilitate the impurity removal, and then leads to the recovery of purified polymer stream. This is on one side of the recycling opportunities. When we look into chemical recycling, it's more invasive process. We can look into solvolysis, pyrolysis, or gasifications, and in all these cases, we go back to oligomers, or we produce oil gas or even a syngas, and after that, for a future valorization, the polymers need to be made again. So in our process, we focus on solvent-based recycling because we would like to valorize already the energy that was invested into making polymers, and then to be able to apply them for further applications. Just a brief introduction into the dissolution process. So at the beginning we have a polymer with certain additives that are added to provide variable properties to the plastic. In the dissolution process, together with a solvent, the process allows for the separation of polymer and additive. In a Plast2bCleaned process, we rely on a single low boiling solvent that is used above its atmospheric boiling point. It's then a pressurized system, and it allows for the dissolution of the targeted polymer in the plastic. We can then remove, separate the additives, and at the end we recover polymer additives, and we can also recycle the solvent. Main benefits of this process are, of course, the energy efficiency. Because of the low applied temperatures, we don't need to separate solvents. We can recover polymers of high quality and ensure the value retention. And we can, of course, also potentially recover and further valorize additives. In dissolution process, we recovered polymers that have not differ in the chain length compared to the material before the dissolution process. So analysis was made, and no variation in molecular weight was observed. It's important to be noted that dissolution process itself cannot improve the quality of the polymer. So if we already have a degraded polymer stream that enters the process, we can only recover it as such. But important, the dissolution process is not further affecting the quality of the material of the polymer, and it's not degrading this polymer. In this process was bromine flame retardant and also antimony trioxide were suspended in the solutions, and we have about approximately 2% of insoluble fraction. For a remover of antimony trioxide, we tested several routes. So there are multiple approaches that have their benefits and drawbacks. So we can rely on sedimentation, centrifugation, even decanter centrifuge, and they showed good separation when tested on a reference substrate. You can see on the left-hand side picture that sedimentation tests were performed as well as centrifugation tests on the right-hand side, whereas centrifugation test led to better results. The drawback of sedimentation test is a long time needed to achieve significant separation of antimony trioxide from polymer solution. And on the pictures completely on the right-hand side, you can see the recovered ATO fraction of a high purity and a low bromide content. For the antimony trioxide, we relied on the on the fact that particles do not dissolve in the selected solvent and remain suspended in the solution. And because of their high density, ATO shows sedimentation behavior, as you can see on the pictures. So on the left-hand side, we have dissolved HIPS solution and HIPS containing ATO. You can see the milky white solution when ATO is present. And after sedimentation, that took about 3 days, so 72 hours, you can see the A2 particles predominantly sedimented at the bottom of the flask. There is still some discoloration of the solution, so it's not fully separated, but the majority of the A2 will sediment. And on the right-hand side picture, you can see the results of the centrifugation experiments after 10, 30, and 50 minutes. And you can see that with increased time, the ATO can be fully separated and found at the bottom of the flask. And please.
Thank you, Lucy. As Lucy has told you just now, you know how the dissolution of the old plastics was done and how the antimony trioxide can be removed. The next step is how do we remove the bromine flame retardants. And here, well, we tested several approaches. Also, we're using supercritical carbon dioxide. But here we want to show you the results that the most sense to us made to use membrane filtration. Why is that? When we look at the standard bromine flame retardants like TBBPA, TTB, we see that we have a molecular weight of between 500 to 1,000 grams per mole, while the ABS usually has molecular mass of between 100 to 300,000 grams per mole. This huge difference in size actually makes it lenient to use a filtration method. And as you can see in the graph in the center, the polymer is retained before the membrane, while the bromine flame retardant, together with a considerable part of the solvent, goes through the membrane. So this is one method we investigated to separate the bromine flame retardants. Well, in theory, it's very nice. In reality, I think in the audience there might be some people who also worked with dissolved polymers. It's a very tricky subject to technically handle, but the team for Plast2bCleaned developed a hot membrane filtration technology that overcame these challenges of a very high viscosity material that tends to form gelation, gel-like material. And on the on the left-hand side of the picture, you see this gray dissolved material containing the polymer and the bromine flame retardants. And on the right-hand side, you see quite a clear permeate. That is the material that goes through the membrane, and the recovered sample of bromine flame retardant, in this case from the reference samples. Going to the next step. Once we remove the bromine flame retardants, we still need to separate the solvent from the polymer. And this is also not an easy task to achieve, because we use the solvent, or we chose the solvent because it has high interactions with the polymer. That means drying it, removing the solvent, is also quite tricky. When you think of, let's say, traditional drying methods like using an oven or a rotary evaporator, you will see on the right-hand side, there should be a little video starting, that it's a very viscous gel-like material. We experienced that while drying, usually the outer layer dries up, and it forms sort of a solvent pocket, we called it, where the solvent still remains inside. What is obviously possible is to use a vacuum extrusion. Here you have high shearing forces, quite high temperature with a vacuum. So this is one possibility, but for Plast2bCleaned we pursued another approach using spray drying. And we tested this with success. On the bottom hand side you can see some spray dried material. And the next slide shows you that with spray drying, starting with a roughly 10% polymer solution, cleaned polymer solution. We sprayed that and removed it within one step over 99.9% of the solvent. And if we later on add some additional extrusion, we reach our target of below 1000 ppm, which is sort of a processing target. Below 0.1% of residual solvent is very important for further processing. What is to mention here is also that those numbers are actually outdated. In the last campaigns that we ran, we actually managed to even go below the 0.1% with just the spray drying. So I think here we're on a good track, and obviously we want to further pursue that. And I will give the word to, sorry.
Yes, I'm taking over again. So based on the test and process development we presented on previous slides, we came to a process flow of Plast2bCleaned process as depicted on this slide. So on the left-hand side, you can see the reference plastic in this case that enters the dissolution process. After that, we perform a coarse filtration step when we separate all insolubles. Further, we pursue with centrifugation to be able to remove ato fraction, and we should also say that in this fraction also insoluble flame retardants will end up. Then the polymer solution ato-free or predominantly ato-free goes to hot filtration, where we recover two streams. Permeate, which after evaporation provides soluble BFR fraction, and from the concentrate, after spray drying, we can recover ABS or HIPS or whatever polymer we focus on in this process. For antimony trioxide, as already mentioned, here on the picture you can see the nice white powder recovered from the reference material. It was of a high purity with a low bromine content. For the polymer product, we also managed to have a very low bromine content. We achieved a bromine reduction of 95%, and residual solvent was below 0.5%. That's already mentioned by Sebastian. These numbers were even further improved down the process. And for antimony, for the soluble brominated flame retardant, we recovered the stream with antimony content below the level of detection. Yes.
And I'm taking over again. I want to take you kind of on a journey of this whole project. We started a bit more than 4.5 years ago, and as you can see on the bottom left-hand side, the first solvent screening was done in a very small lab scale. Then we took it was further scaled to the TNO Mobius reactor. Then at Fraunhofer we had the first membrane trials, and on the bottom right-hand side you can see the plant that was basically built on this project, the Plast2bCleaned project, that has a capacity with 15-liter reactors, so we can process kilogram scale material here. And well, you see the chronological arrow here. I think it's just nice to see where we started and what we achieved in 4.5 years, and hopefully we'll get the chance to move this topic further. And I'm gonna basically show you the same thing that Lucy showed you, but in this case, it wasn't on reference material, but on sorted waste. So it's kind of hand-picked waste from CRT, back screens. Well, and as you can see, we start with the sorted waste. We do the dissolution, we do the coarse filtration. Here again, we have about 2% insoluble material. Unfortunately, truth be told, that the antimony trioxide fraction is still roadworks ahead for us. It doesn't look as nice as the results we had on the reference material. But when we look At the recovered ABS, we still have quite good results. We reach residual solvent content below 0.2%, and unfortunately not the 95% bromine reduction, but the 73% bromine reduction in this case. Still a good target and some, well, good starting point to do further development. Also, the bromine fraction we recovered, you saw the picture before, it was a nice yellowish granular powder. Obviously, when we turn to the real world, to waste, even though it's sorted, real waste, you see that there's a lot more additives in that make this fraction a bit tricky. But this is something that our partners ICL actually are looking into, how to process that into bromine that can be used. And I think that, oh, yep, sorry, I thought that was you.
Yes. So we moved to the material we actually managed to recover in the RL5 plant. Here again, the picture of the nice pilot plant that is standing at Fraunhofer, and it allows testing and processing in a kilogram scale. As said, it was a joint development of Steno and Fraunhofer with engineering support of Juchheim. And it was you. Sorry, we will switch.
Sorry. And I just want to take you along the journey of how we processed everything at our TRL5 plant at Fraunhofer. We used sorted waste. You can see different buckets there, because they were from different starting material. In the end, we mixed them in specific ratios to be closest to reality as possible. We performed the dissolution on it, so we used the sorted waste, put it in the reactor, added the solvent, closed everything, heated it up. And as you can see, it dissolved, and there will be a video starting, the top side video. There you can see the dissolved material leaving this pressure tank, and what's nice to see is that there is no gelation, no gel formation, no residue within this reactor, which is a good sign for a possible process routine there. It goes through a bottom outlet along a coarse filter, and in the coarse filter we have the 2% residue that was not dissolved. It's filtered off and later on removed out of the process. Then we move to the next step, the sedimentation at our TR5 plant. Here the antimony trioxide was removed via sedimentation, and here how we realized it was attaching a height adjustable dip pipe, so let it settle for a while, and then remove the supernatant, so the upper layer with the lower antimony content, and push it through to the next vessel. And in the next vessel, from there we start the hot filtration, the hot membrane filtration that I explained before. Just to take you along here, remember it's a mixture of dissolved polymer and bromine flame retardant. They're circulated in a circle, and they pass along 3 membranes that have a length of 60 centimeters and a total filter area of together 1 square meter. And as I said before, the bromine flame retardants, as their smaller molecular weight, go through the membrane and are removed with the permeate. The permeate in this case is the fraction that goes through the filter. And the purified polymer remains in the concentrate, and sooner or later also thickens a bit. Here you see the picture I've shown before, but I think it's nice to see again on the bottom left-hand side, you see the concentrate, which is a gray non-see-through material. The permeate again is see-through. It does have different colors depending on the feedstock. We tried over the course of this project several feedstocks, and the permeate ranged from pink to yellow to orange to purple, so we had a very colorful outcome here. But the important part is we had a see-through permeate fraction that had a high BFR content in the end. And in the middle picture, you just see a little GIF or a video where the permeate accrues. Okay. Moving on to the last step of the process, the spray drying. Remember, now we have a purified polymer in the solvent. How do we separate the solvent and recover the polymer? That's done by a spray drying unit situated at Fraunhofer ICT. And the purified polymer is dried, is sprayed through a nozzle, and this thereby forms small droplets. These droplets dry and make a very, it has not been mentioned before, a very fluffy consistency dried ABS. And the facility is located at Fraunhofer ICT in Finstal in southern Germany. And, well, as you saw before, the first 3 steps are done at the new built plant. The 4th step, the spray drying, is done at a separate location. So there we have to move or carry the, transport the purified polymer solution to the spray drying unit. And, yeah, sorry.
Yes, so let's summarize. So in TL5 plant, we started with sorted ABS, as you can see on the left-hand side. So this is ABS stream coming from post-consumer recyclate. And this feedstock is then entered into the pilot plant, where the dissolution, sedimentation, and membrane filtration takes place. At the end, we have a purified polymer solution that enters a spray drying step, and as a result, we recover recycled ABS, as shown in the right-hand side picture. Very fluffy material. Lightly gray because some of the pigment were still in the product, and at the end, test bars were made out of a recovered polymer to do mechanical testing and evaluate the properties of recovered ABS. And here a bit small video how the okay. Yeah, so the video is starting now. You will see how the polymer powder is processed in the extrude, to be pressed and molded. No, it's in extruder, sorry. So it will be extruded and at the end chopped into small pellets. And here are already the chopped pellets, which will be further injection molded into test bars. So let's see if the video will start. Yes. Yes, it's starting now. So you can see now the process, how from the extruded polymer pellet, a test bar is injection molded, and here the test bar is falling down, and it will be used later on for mechanical testing. And just briefly to say that the recovered ABS pass reach SVHC and also pop test. And for the mechanical characteristics, we compare the recycled ABS to 2 different virgin grades of ABS of the Helix Polymers project partner, and all the characteristics are performing pretty well compared to the virgin part. Only the impact strength is lower in case of recycled ABS and needs to be further improved in a recompounding step. And just to say, at the end, we recovered about 9 kilos of recycled ABS that was further densified and sent for recompounding to Alex polymers, and Alex polymers provided recompounded ABS to Electrolux for production of prototypes. And on that process, Marco will walk you through.
Okay, so in the end, we were able to use the material after recovery from scraps, and the final step, of course, is to really produce some parts, and that's exactly what we did. We just used the prototype mold for a porthole frame for a washing machine, and what was really important that first of all we really used the same operating conditions typical for a virgin ABS. Of course, due to the high fluidity of the material, there were some bursts, some more bursts than expected, but there was a very high gloss, so the quality of the surface was very good. And there was no visible defect on the surface. That was very, very important. At the same time, taking advantage of the high fluidity of the material, we just tried to reduce a bit the temperature along the cylinder, and that was also possible because it was in reality an improvement in the process, because there was an increase of pressure, but the temperature was reduced of 15-20 degrees. Practically very small differences in the filling pattern, a small reduction of the bars, of course, it was good, and again, a negative aspect was the visible welding lines were still increasing a bit, but that was a prototype mold, and as you can see in the photo, there's a typical injection system which is not used for the industrial production. It's a different approach to produce such kind of frames. As you can see in this photo, we used this prototype just because there was the opportunity to really see different textures. So we have in the same frame clean surface, high gloss, matte surface, but we had 3 different textures on the same surface. So we were able to evaluate how the material was able to really fill the cavity and give the expected aesthetics. Most of all, there was no dimensional change in the frame, so no deformation of the frame, and the behavior was identical to the one expected for the virgin ABS. So replacement one-to-one was really viable, possible. Another key part for us is also the possibility to paint that frame. We have some versions, some appliances where we apply a wet paint on the surface, and the characteristic of the surface needs to be, let's say, to fulfill some requirements. And the good point was that the distribution of the paint was good. Again, no defects on the paints because the surface tension of the material was unchanged. So the adhesion of the paint was good, and you can see in the photo on the right side that the typical test of cutting, the cross-cut test, cutting the surface and removing with an adhesive tape the arteria was really positive. There was no detachment of the paint. And again, that was a very, very good result. But besides that part, which was focused on the aesthetics, on the paintability, on the dimension, another key part was to evaluate the behavior of the frame when assembled in a full porthole. Okay, and in comparison with the same appliance, but with a porthole with a virgin ABS. You can see in those photos, on the left, the typical white frame, and on the right, the grayish, dark gray frame produced by using our Plast2bCleaned ABS. There was no problem in assembling that porthole. There was no deformation, confirmed. There was no problem in screwing that frame together with the back frame, and everything was fine. No change for assembly this porthole. Again, good point. Next step was to test the behavior of the assembly. And that is usually done by really making some, let's say, stresses on the porthole in a appliances. Okay, everything's fine. Yeah, in this case, there was a testing machine which really forced the porthole in, let's say, unusual direction, in a vertical way, in torsional way, and simulating a misuse when the porthole is closed and someone tries to let's say, push back from the back position, from the back, the same porthole. The results were expressed as a displacement, deformation, versus the force applied. And again, we didn't see any change with respect to the virgin ABS. So very, very good results also in this case. So now I leave Lucy to the conclusion.
Thank you, Marco. So I think that the results speak the loudest, so I hope that Marco convinced you that the product that we received from the Plast2bCleaned process has very high quality if it can compare to virgin ABS and make it into prototype without alternations of the process. Here I will just briefly summarize what we have achieved technically in this process. So we managed to develop a process that relies on low boiling single solvent and allows for the separation and recovery of polymer and additives. Antimony trioxide was recovered with high yields from reference material, and these results were unfortunately not achieved yet on sorted waste samples. With hot filtration, we managed to recover brominated film retardants with high removal efficiency, above 95% on reference materials, a bit lower, 73% on sorted waste ABS. Recovered polymer was of very low solvent residue, typically around 0.1%, and recycled ABS pass all performed as REACH as VHC and POP, and only impact strength needs to be improved in recompounding, which has been at the end achieved and allowed production of 24 prototypes of washing machine door frames that were successfully produced and tested in operating conditions and compared to virgin ABS grade. And as already mentioned, no effects on the mechanical performance of these prototypes has been observed. So with this, we finished this section. So maybe if there are any questions.
Hi, me again. I think you can hear me now. Yes, sorry to jump in, but actually we have a question. So I'm very happy that you launched that question through the chat. I will release the question and see if our speakers can answer the question. I really hope you enjoyed the session. If you have other questions, you can always ask them still on the chat, and we will come back later with those. So please continue participating on the chat with the questions. Well, the question they raised, it was from Hans Brouwer. And the question is, have you considered precipitation as an alternative to spray drying?
Yeah. Yes. Precipitation using an anti-solvent is a well-known method. We wanted to. It is a good process. It has its benefits. It has some drawbacks, and we wanted to go a different way. And when you use precipitation, you usually end up with a very sticky material that's hard to filter, while we stay in solvent, the filtration is easier, and later on, the spray drying turns out to be, hopefully, the last, information needs to be sorted, but hopefully a more energy efficient way of drying the polymer material. I hope I answered that question. Of solvent recovery, sorry.
I will just add on this one. So one of additional drawbacks of using anti-solvent to precipitate the polymer solution is that at the end of the process, you need to separate a mix of two solvents. And goal of our process to be also energy efficient and possibly economically viable. And if you need to separate two solvents, it leads to higher energy needs. So that was also one of the aspects why we chose spray drying as a final processing step.
Thank you very much. We really hope that question was answered. If not, and you can see there that you would like to know further, you can always ask on the chat. Thank you very much for your interesting questions and participation. We will now move to the next presentation. I will introduce the speaker. You saw her before on the speaker list. She is Zainara Pocheville from Geiger Technology Center, and she will be speaking about the pre-sorting using RAMAN spectroscopy and machine learning. And now, Zainara, the floor is yours.
Thank you, Mariana. So good morning. I'm going to present you the result that we have obtained on pre-sorting WEEE plastics using RAMAN spectroscopy and machine learning methods. First of all, I'm going to introduce the problematic with WEEE plastics recycling. These type of plastics are nowadays treated in an industry by mechanical separation using several sorting technologies like near-infrared spectroscopy, density separation, or electrostatic separation. However, a large part of WEEE plastics are nowadays not recovered and end up incinerated. Why? Because there are some technical barriers, mainly with the usual spectroscopic technologies. There is an incorrect identification of these type of plastics, because WEEE plastic contain high loads of additives like pigments such as carbon black or brominated frame retardants and other fillers. And also because recyclers receive a complex mixture that it is composed not only of plastics but also of PCBs, metals and cables. So there is a challenge to improve WEEE plastic sorting, and that's what we have researched on the Plast2bCleaned project. So, first of all, with our industrial partner, Currec, who is the recycler, we selected the most challenging WEEE stream, that is the sinking fraction. This fraction is obtained after the density separation process. It is composed of heavy plastics. It is rich in brominated frame retardants, and as you can see on the picture, most of these plastics are dark or black. In this WEEE stream, we can expect 10% of polystyrene and also 10% of ABS on average. So this is the content of our target polymers to improve the sorting. But there are other polymers that could be of interest for the recyclers, that, like the blend PC ABS or PC. But there are other polymers that can jeopardize the sorting of the target polymers for the Plast2bCleaned project. On the other hand, in the beginning of the project, we also defined with the industrial partners which were the requirements for the sorting method. That is, if we want to further scale up the classification method to improve the identification of the WEEE plastics, we have to consider the technical requirements of the recyclers and also the quality requirements of the end users of the recycled plastics. And for that, we defined that our sorting method should achieve a classification and purity rates above 80% for each sorted target polymer. Also, as we went to scale up the process, we defined that for the automation of the classification process, we have to develop a model with short measuring times for each measure. So, with these premises, we start working on analyzing WEEE plastics with the RAMAN spectroscopy. This technique is an analytical technique that uses a laser as a source of high intense monochromatic light. That is, one laser has a certain wavelength, and it is using for chemical identification of compounds. For the Plast2bCleaned project, we acquired 2 RAMAN spectrometers with 2 different lasers. One laser had a wavelength of 785 nanometers and the other laser of 1064 nanometers. If the target is with the RAMAN analysis to obtain a high quality RAMAN spectrum. If we get that, we can identify a compound chemically. On the pictures on the right, you can see that we obtain clear spectrum for reference polymers or transparent or light colored plastics. However, when we analyze the WEEE plastics, we obtain the fluorescent effect. Fluorescence overlaps the characteristic bands of the polymers, so it was very difficult to discriminate the target polymers only with the RAMAN spectrum. Nevertheless, between both wavelengths, we define that with a laser of 1064 nanometer, we get less fluorescence in the RAMAN spectrum of WEEE plastics. So, it was clear that we had to combine the RAMAN spectroscopy with machine learning techniques to develop a classification model. Machine learning techniques are mathematical models, algorithms that are used in spectroscopy to remove all the unwanted signal like fluorescence or background and to define patterns in a group of samples. So we have used these techniques. And first of all, we analyze around 500 WEEE plastics with a laser of 1064 nanometer at 1 second, and we build a spectral data set. With the algorithms, we are using commercial software called Unscramble. We preprocess those spectral data, and we train several models to define a prediction model that could sort 4 categories in one step. In this prediction model, we included a category for polystyrene, another category for ABS, which were the target polymers for the Plast2bCleaned process, also another category for the blend PC-ABS, and a 4th category for the other polymers that we want to sort from the target plastics. With the multivariate analysis, we train several models using linear discriminant analysis and support vector matching methodologies, and we obtain different rates for the classification and purity. We didn't reach the industrial requirements that these rates need to be above 80%, but we want to move forward to automate the classification process. So we selected one of our best performing model, which is based on linear discriminant analysis, and with this model we reach at least a purity of the sorted polymer of 80% at lab scale. we gave priority to select a model with high purity to get sorted polymers with less contaminants. So next, we designed and developed a RAMAN sorting prototype. This prototype was set up at Geiger. And here, just we couple our bench scale RAMAN spectrometer under a conveyor belt. And we can make online RAMAN measurements and the online classification of WEEE plastics because we have also developed a dedicated software implementing the model. So to test the model at TRL5, we selected different WEEE plastics, different event data set from TV back covers and monitors, and we obtained different classification results. As you can see here, we improved the classification rate a little bit for the sorted PS and ABS. However, the purity was lower than a lab scale. In this moment, we collaborated with a TNO expert at data analysis, and they have also explored other machine learning models that artificial neural networks, random forest or ensemble models. And with the pilot RAMAN spectral data, they have trained a model that could sort ABS with a purity around 75%. So this result was more close to the result that we have obtained at lab scale. So our main conclusions and results are that, first of all, as we have developed a RAMAN sorting prototype, we have demonstrated that a RAMAN spectroscopy with machine learning techniques can be used in real-time application, in this case for WEEE plastic sorting. And the innovation is that we have used a laser of 1064 nanometer, acquiring a spectrum at 1 second. We have also developed several classification models to sort polystyrene ABS and a blend of PC ABS from WEEE stream. However, as an overall result, we have obtained a trade-off between the classification and purity rates, as they were not achieved at the same time. However, black plastics were partially identified. Nevertheless, these are still a challenging WEEE stream. So further research on WEEE plastic classification is needed using the RAMAN spectroscopy. We have to explore alternative pilot testing scenarios, new spectral data processing, and also be aware of a new technological solution, mainly related to the optical systems, to reduce the fluorescence and to get a RAMAN spectrum of higher quality. Also, another further research could be to combine sorting strategies to increase the purity of the sorted polymer. So thank you for your attention, and Mariana will tell us if there are any questions.
Thank you very much, Ainara. Very interesting presentation. Indeed, there is a question, but I think it comes more for the previous presentation. I saw it on the chat. That question will be directly answered on the chat if you agree. But anyway, if you consider that the question is not answered, again, please don't hesitate to tell us, and we will try to address it later. And now we will move on to the next presentation. It will be my pleasure to introduce my colleague Espela. She will be speaking about the impact assessment. I know probably the questions will come after the presentation, as we had this question before, but no worries, our speakers can address those later, so continue please asking questions. And now I will leave the floor to my colleague Espela. Espela, the floor is yours.
Thank you, Mariana. So in this project, we conducted life cycle assessment and life cycle costing to assess the environmental and economic feasibility of our process. We have a lot of stakeholders in the project, from recyclers to end users, and that's why we decided to conduct the analysis from two perspectives. One perspective is the waste perspective, where we evaluate what are the environmental impacts and costs of treating 1 ton of WEEE electric and electronic waste plastics through the Plast2bCleaned process and comparing it to the incineration. On the other hand, we have a product perspective where we evaluate what are the impacts of using recycled material in a specific applications and comparing it with the usage of virgin material. And in this case, our application is one piece of the washing machine door frame. If I move on directly to the LCA results, focus on the carbon footprint, we see that from the waste perspective, Plast2bCleaned process, including with the improved sorting, performs 226% better than the incineration with energy recovery. In fact, it has a big contribution of negative emissions which come from the recovered polymers from the dissolution technology. This is in the graph indicated with the gray bar, but we also included negative emissions from the recovery of non-brominated plastic that are also separated and possible to recover, and they constitute a large part of the waste stream. If we move on to the product perspective, we see here the carbon footprint of one piece of washing machine door frame with a different percentage of recycled ABS used in the piece. So if you're using 50% recycled ABS and 50% virgin ABS, we see that the carbon footprint reduced to 35%, for 35%. And if we increase the share of recycled ABS to 100, we see that also the reduction potential is doubled. In addition to this base case scenario, we also conducted sensitivity analysis where we changed the inputs of certain parameters in the process. We increased the energy usage and solvent losses. And so that's why the carbon footprint of the Plast2bCleaned process increased. And even though it increased in comparison to the incineration, the Plast2bCleaned process performs still very good, 188% better in comparison to the incineration. The same goes for the product perspective. We still see the reduction in the carbon footprint, but it's reduced to 24% when used 50% of recycled ABS and 48% when there's 100% recycled ABS used. If I move on to the life cycle costing, here we have the cost breakdown of the Plast2bCleaned process from the waste perspective. The market price of ABS is subtracted from the total costs of processing, so including sorting, dissolution, and the incineration of all the losses. And we end up with a total price of 21 cents per kilogram of processed waste. That means that we are in the end saving 79 cents per kilogram of waste because we are avoiding the costs of the incinerations, which are €1 per kilogram. And from the waste perspective, we can conclude that the process have a positive economical outcome. The same as with LCA, we try to test what is the cost sensitivity to the process changes. we see that if we increase the energy cost and also the personal expenses, we see that the process still has a valid business case. However, in case when the solvent losses are increased, we see that the costs surpass the break-even point and we have added losses. And in the worst case scenario where all the sensitivities kind of come true, the process experiences loss of 570 euros per ton of process waste. So from this graph, we see that there's a large cost variability depending on the process situation. Moving on to the product perspective, here we see the breakdown of the price of costs of producing one piece of washing machine door frame. And we evaluated two scenarios, eco-friendly scenario where we include only recycle ABS in the washing machine, and the worst case scenario where in the price is included all the energy increase, labor and chemical costs. And we see that in both cases actually the production of the washing machine with the recycle ABS has higher costs than the production of the virgin one. In the eco-friendly scenario, the increase is in 8%, and in the worst case is 46%. So what can we conclude from all of this? That is that from the more societal perspective, there are significant CO2 savings from the Plast2bCleaned route, including the dissolution technology and the improved sorting compared to the incineration. And also the carbon footprint is not so sensitive to the process changes that we studied in the sensitivity analysis. Looking at the life cycle costing, also from the waste perspective, it is possible for Plast2bCleaned process to operate in an economical manner ranging from savings up to 760 euros per ton to the added cost of 570 euros per ton, again in the comparison with incineration. But looking purely from the business perspective, it is actually more costly to produce recycled ABS than the virgin one. Overall, a message is that from the societal point of view, it's still worthwhile to invest in the technology. There are big CO2 savings, and it is a possibility that in the future, when the CO2 tax is implemented, that also the Plast2bCleaned technology can operate in economical manner. Yeah, thank you.
Thank you very much, and sorry because I have to go on the stairs, and that took a minute. Thank you very much, Spela. Very interesting presentation. I know sometimes the LSCEC and LCA are the most complicated part of a project, and questions could come later after people doing some thoughts on that, because right now there is no question on the chat, so maybe this will come later. And now we will move then to finally our impact for Europe. And we are waiting for our speaker now. Tom Carris will be in charge of this presentation. Tom, the floor is yours.
Yep, thank you. So for the potential impact on Europe, if we look at European policies, we see a lot of legislation coming at us, plastic strategy, circular economy targets, waste, toxic-free environment, you name it. So there is really a lot of European legislation coming at us as recyclers. But looking from the perspective of a recycler, you know, this is what our main stakeholder often looks like. It's like we're being hunted. On the one side, we should recycle more. On the other side, there is too much hazardous substances, and we have to be more careful about it. We have to provide more proof. So it's really a scary environment to be in. There was a study performed by DSS Plus last year for BSEF, in which they have been looking where is WEEE plastics being generated and where is all that WEEE plastics going. So what you see from the total of 2.6 million tons of WEEE plastics generated in Europe alone, you see that only roughly 160 kilotons is actually being recycled today. There is waste coming from there. There is plastics earlier in the chains that in the recycling chain that are leaving Europe. There is a lot of WEEE that we don't even know where it's going, or that is going into the wrong direction, into the municipal waste, into the metal scrap, and so on and so on. So if you look for that total of 2.6 million tons of potential input to recycling, we see that the vast majority is lost today for recycling. So if we then look at what is then the potential for Plast2bCleaned technology on all these volumes, you know, you can add this up and you come to more than 1.5 million tons as potential input to Plast2bCleaned process. With that potential, looking more into detail, where are then the WEEE flows that might be interesting? Coming from the same study again, you can see that the biggest potential of brominated plastics is then mainly in the screens, in the small appliances, and in the IT. Adding that up, taking the previous picture in account, we have a potential of 77 kilotons that could be recycled with Plast2bCleaned process in Europe. On screens and on small IT equipment, this could be a potential increase of 2.5% to 3% in recycling rate. Now that doesn't sound like a lot, but I can tell you we have to fight for every 0.1% in increasing the recycling rate. So having a technology with this kind of potential is really significant for recycling. So that, in a nutshell, is the potential that we have with this technology, and I'm open for your questions.
As you can see, our speakers are moving fast. We are earlier than expected. So that means that we have more time for our panel discussion. You see on the screen the name of the speakers, but anyway, I will remind who will be participating today on this panel discussion. And Judith Kessens, our project coordinator, will be moderating the session, and then we will be having, and you will see that the camera will move to see the panelists. We have also Tom Carris, Roland Johnson, and Marco Garilli. They will go through the Plast2bCleaned process, but that doesn't mean, again, that you cannot participate. Please ask as many questions as you consider to join this discussion with our panelists. So now I will leave the floor to Judith so she can start moderating the session. And I invite all the speakers to please join the scenario here with the different microphones so you can take the lead on the conversation. So please come here and join us.
Thank you, Mariana. Okay, very welcome to this panel discussion on the Plast2bCleaned project. Now we know what the results are. We like to discuss a bit more on how are we going to use it after the project and what does it mean. And therefore we have a panelist with potential end users of our technology within our consortium. First of all, a bit more about myself. My name is Judith Kessens. I work at TNO. And I'm a senior project leader. I have a background in physics and I also did a PhD on speech recognition. And now I'm working in sustainability with a lot of fun and a very impactful topic. And I'm leading several projects within the field of circular plastics, of which this is one. Then I like to introduce as well the panelists. First of all, we have here Tom Karis from Coolwerk organization. Tom Karis is manager business development within the Coolwerk group, and Coolwerk is part of ReNewWe. And Coolwerk is active within the Benelux area and is responsible for recycling of plastics from WEEE back into products. With customers within the toy industry, I heard Playmobil, Tom, and also the electrical appliance sector. And Tom has a background in mechanical engineering, and he has a lot of experience in operational functions in the production industry. Besides research and development, Tom is also very active on regulatory aspects. So he is, for instance, in the board of the European Electronic Recycling Association and in the board of the Plastics Recyclers Europe. Then our next panelist is Roland Jansems from the ICL group. Roland is a Product Stewardship and Sustainability Manager at ICL Group for in the industrial products. He is, has experience in environmental science and life cycle assessments, and he has also worked in the chemical manufacturing. ICL is a global leader in elemental bromine production, and the industrial products division provides solutions for fire safety, personal care, food, e-mobility and renewable energy, and at the same time embracing innovation, progress and prioritization sustainability. But you will definitely tell a bit more about that aspect, Roland. Today, Roland's focus is mainly on plastics containing BFRs to support the recycling activities and projects in Europe, like in this project, the Plast2bCleaned project. And Roland is also active on regulatory aspects and involved in standardization activities and working groups. And then I also like to introduce the final panelist. It's Marco Garilli from Electrolux. Marco works at the as a plastics material expert at the Electrolux Product Technology Labs located in Italy. And we are currently here in Electrolux, that's the place where Marco is working. The work of Marco is mainly focused on the application of sustainable plastics for Electrolux appliances. And Electrolux contributes to the target set by this company to have 50% of recycled plastics in appliances by 2030. And I guess you will elaborate a bit on that later on, Marco. Marco has a background as a chemist, and he has experience in the petrochemical industry and also in the automotive industry, and especially with a focus on plastic components. And in both cases, he was part of the research and development team, and he led several projects, mainly with transnational teams, as is the case in this Plast2bCleaned project. At this moment, Marco is leading a team in Electrolux, and this team is focused on the recycling of plastics for appliances, and of course he is active in this Plast2bCleaned project. So I hope this gives you a bit insight in the background of the panelists. And I like to start with questions. And please, if there's questions in the audience, put them in the chat and we can involve them in this discussion. But my first question is about the ambitions of the companies which are represented here. You heard something already in my introduction, but I like the panelists to tell a bit more about the circular ambitions that you have within your organizations and possibly the challenges you encountered. And maybe I like to start with Tom, because Tom, you told earlier in a conference where we were together that recyclers need to become secondary material producers. Maybe you can say a bit more about that.
Yes, indeed. Thank you, Judith. First of all, why we are doing this from our company and our mother company, we are a waste management company, but we are one of the few waste management companies that doesn't have own incineration capacity. So what is very important for us is that we incinerate as little as possible, that we recycle as much as possible, because a waste management company that owns its own incinerators is always incentivized to fill that incinerator to the maximum, because that's a huge capex investment. So for us as a company, the main objective or the main reason why we participate in projects like this is to be able to recycle as much as possible. And if you remember from the presentation I just gave, in the second slide you had this mass flow diagram. You saw that roughly half of the WEEE plastics that we receive are still a waste today. And with a project like this, or with a technology like this, we would be able to recycle much more of these plastics that we can't recycle today. So that is definitely why we are doing this. Then the second point where you say we have to become material or producers or secondary raw material producers, it is a bit... When I started in the waste business, I saw we were very much a business of, well, we throw everything on a pile, we throw it to our production lines, and then we try to sell what comes out of that. If you want to go to end applications like electronics, like with Electrolux, like the porthole we just produced in this project, you need much more than just, trying to sell what you are producing. You are then producing something that has to have a consistent quality. You need to have a guarantee about compliance to chemical legislation. And in order to do so, we need a mentality change in recycling and waste management companies to get more this producing mentality and much less of this waste mentality that we sometimes still have.
Mm-hmm. Like waste no more.
Waste no more, indeed.
Okay, thank you so much, Tom. Then I like to ask the same question to Roland. What are your circular ambitions and what are the challenges?
Of course, our circular ambitions are to be part of circular economy. Our products have a very specific properties why they are in plastics. So it's a flame retardancy. And as Tom already presented, it's around 3.5% of WEEE plastics contain some sort of brominated flame retardants. And our ambition, of course, is to support recyclers and producers to close this loop and recover the bromine for potential new, more sustainable solutions. So I'll keep my answer a bit shorter than Tom.
Short and clear. So then there's more time for Marco. Marco.
Yeah. Yes, I think that the target is clear. 50% of plastic within 2030. It's a clear target, but it's also a challenging target. So it's not easy. It's to use in reality, and we have seen also from the results from Spela that the business case is not really robust. Okay, so we need to further improvement in this direction. And if at that stage we see some problems, you can imagine when we have to apply the material into a real component, into a real appliance. So the target is clear, the target is challenging, but we don't want to, let's say, lose momentum on this, because it's very important for us to really stay in touch with the future, because it's very important. We all also need to, let's say, to stay in touch with the latest developments for recycled plastics. We already use recycled plastics, mechanically recycled, but we need to do more and to really see the opportunity to use recycled materials coming from different approaches. Could be the physical, or let's say, solvent-based recycling, okay, like this. Could be the chemical recycling as well. But in our vision, we need to take together all those opportunities in one only, big one, okay, which is being really circular. Which is not using a recycled material and then you produce something that in the end go to the incineration. No, we need to close the loop. And this means that we need to collaborate efficiently with the other companies like Kurek, like other companies interested in recovering other materials, flame retardants and so on. So, the scenario is not just limited to some plastics, some recycling, but it's wider. And of course, we cannot afford to have a very high cost for that, because if nobody buys the appliances because the cost is too high, so then the final target is not there. So it's very important to consider all the problems, all the issues, but in my opinion, every problem, every issue is always an opportunity, and we need to go this way and keep this direction.
Thank you, Marco. So I think from all of the panelists, there's a clear need for this technology, and there's still some challenging to overcome. But if we look at these specific outcomes and results we have seen, what do you think are the next steps for this technology, for the Plast2bCleaned technology? And maybe, Marco, we can start with you now.
Yes, I think we see that we can successfully use the material, okay? That there are no problems, that especially with such kind of materials we can do something really important. Not only for our target, but in general terms. We also know that we need to be more effective in really making this process a real process, large-scale process. Scaling up is very important, because we have seen that starting from the very little lab, let's say, equipment, we achieved some results, and then scale up, maybe the things improved really. So we really need to raise the technological readiness of the process. It's very important, because we only at that level we can really see what is the real business case, what is the real cost of the material, what are the real opportunities for the market, for the real implementation.
Yeah, thank you, Marco. Is this also the way you see it, Roland? Scaling up, that's the next step?
We definitely encourage scaling up, because like Marco said, then you really see what's going to happen with the whole process. It needs to be continuous, and then we can feed large volumes of recycled material and process it. We also, of course, learn from this Plast2bCleaned technology that there is a certain permeate, like Sebastian from Fraunhofer presented, that it's containing dissolved brominated flame retardants, and we have learned that we have the capacity to recycle it. So this part of a waste stream we can recycle and keep bromine in a circular loop, and we can do that in our Terneuzen site in Netherlands. The other challenges, of course, we see that ends up with the antimony, and that's a next step that we are very interested and keen to learn and develop technology to resolve. And then together with Campin, we have, I think, quite some project coming up investigating that.
Yeah, thank you. And Tom, what's your viewpoint?
Obviously, the upscaling definitely needed to make sure that well, we tackle all the problems that you always get when you scale up to a larger scale. And besides that, we've seen also from the presentation from Ainara that we still have some technical issues in the pre-sorting phase where we definitely need to work. The potential is there, we've seen it, but we need some more work before we are ready to take that next step.
Yeah, thanks a lot. And also for the audience, it's important to know that now this project has ended. We are also looking forward and looking for new opportunities to proceed the work and to tackle the challenges and go to a higher TRL level. So within this consortium, we have already some plans, but if there are some people that are now in this webinar and are interested to collaborate, please contact us and we can see how we can do that together. I like also to know, because we did this work and because of all the work we have also had some experience, good experiences and also some lessons learned. And I think it's interesting for the audience also to know what did you learn? Do you have also recommendations for others or working on the same type of problems, but also possibly for policymakers in order to help the further development of this process? Who likes to react? Maybe you, Tom?
Shall I start?
Yeah.
Well, I think there's two things that we learned at this project. The first thing is the collaborative part, the fact of having industry partners and research partners at the same time, but especially the involvement of the industry partners in guiding the research partners, because let's face it, I don't take it personally, but researchers, very nice people, very intelligent people, extremely intelligent people, but they are researchers and they are not always in touch with reality, which is the case in waste. And it's especially in this case of waste where you have this immensely heterogeneous waste stream where, well, everything you can imagine it's in there and things you can't imagine are in there. And the fact of having to solve that in a project really requires that involvement, strong involvement of industry partners like us at an early stage. And that, I think, is part of the success in this project. The fact that we achieved what we achieved is also because we have been looking from the very early start on what are we going to have to tackle in the real waste, and we took that into account from the very first small lab scale tests. So that's the first thing. The second thing is from a regulatory point of view, and it's more, it's an advice or a tip for everybody who's working in research, but as well for the policymakers at the same time. What we have seen in the project is that we are shooting at a moving target. During the project, the legislation that is regulating brominated flame retardant has changed twice. The limit values that we have to aim at changed twice during the project, and we are now discussing a third change in the meantime. So that is really something that is extremely important, that as a project consortium, you keep an eye on what is happening out there on the European level in this case, but also for the policymakers, they have to make sure that they also look at the projects that they are investing in. Because like you said in the beginning, Europe invested 4.5 million in this project. So it is very important that when they are developing new legislation or when they are changing legislation, that they take into account the technologies that are under development, because with the limit values that they might decide today, they might simply kill off investments or a research that is about to start blossoming.
Thank you, Tom. Maybe, Roland, do you like to add, especially, for instance, the regulation part, as you are active in that?
Yes, we also saw the timeline. Yeah, so starting the project, it takes you 5 years to develop something that's actually could be working. But meantime, basically, the caravan is going down the hill and the horse is still up the hill. So the industry is staying and looking, trying to catch up something that's rolling so fast down. And how can you catch up with your technology that fast? Because it takes time to investigate, scale up, and then make it feasible and economical. Yes, and of course that brings another attention, what are the future restrictions on other types of flame retardants or substances in our plastics or in general waste, yeah? So we have to pretty much see behind the horizon and guess, okay, this is coming up next, so we have to develop something that we don't know yet it's going to take place. So it's definitely a bit a challenge, yes, and a guessing game.
Okay, thank you, Roland. And also good to know for the audience, currently we are writing a policy brief in which we write down these recommendations for policies. It will be publicly available, so if you are interested, please let us know and we can share it with you. And Marco, I think you also have recommendations,
Yeah. I mean,
but maybe from a different perspective.
I'm from the technical side,
Yeah.
so recommendation from the policymakers,
Yeah.
it's not my business in reality. But speaking more as a European citizen, what I see is that still we have a gap between the idea of Europe and what the real Europe should be. So too many countries are, let's say, moving independently from the others within Europe, okay? So legislation starting in France, and we decide you don't want this material anymore. Come on, wait a moment. Let's discuss together. Let's check what's the market, what are the ambitions, what are the targets at European level. Then, Swedish tax, another example, and so on. I mean, this is not acceptable anymore, in my opinion. If we really want a European approach, if you want to be really Europe, okay, in capital letters, we cannot afford this. We cannot, let's say, fight against regional regulations that are not harmonized within all of Europe. Yeah. And in my opinion, that's create problems because I represent a company which sells worldwide, okay? We are not interested in Europe only. We are interested in the overall world, okay? So for us, producing an appliance and taking into account that, sorry, I need to have this material, but not for France or not for Sweden or not for, I don't know, it's out of discussion. So it's a complication. It's really killing the business also in some cases. Okay, so we don't want that. We cannot accept that. And we need to give this clear message to the European regulators because it's very important. It's creating too many problems.
Thank you, Marco. And I was looking at the time. I think we are almost there. So I like to finalize with the last question. And that's the positive side of what did you learn from this project and what opportunities, well, mainly the opportunities do you see for this project results? So Tom?
The main lesson is, of course, in the technology itself. We've seen the potential of the technology, we've seen the feasibility of the technology, and looking forward, I think it will only become increasingly more important for Europe. We see in European legislation, in REACH, in POP regulation, we see more and more substances being added. We see more and more substances that we have to remove in a way from the recycling stream. And at the same time, we have to recycle more. So if we want to combine that, the only potential is by this kinds of technology. And the fact that what we've seen in a project that is, okay, what we have developed now is for ABS, but with some modifications, you can adapt it to other polymers, to other substances, and so on. Mm-hmm. That gives, of course, a huge potential for what's coming at us in the next decade.
Yeah. Thank you. Roland?
Yes, we definitely acknowledge the benefits of Plast2bCleaned process, but of course it brings other realities and challenges of it that further needs to be developed. And as we saw, part of the bromine really we can recover, which is great polymer, we can recover, and with some adding fresh materials we can make great prototypes. But there is a antimony that still needs to be addressed, and insoluble and other additives that are there still needs to be addressed to make it a really feasible case, and yes, further development is needed, and we have to then scale it up.
Thank you. Marco.
Well, I think that I've learned a lot, frankly speaking, and I was really happy to work with this team, because it was a very key experience for me. Okay, from myself, and I think that it's also important as a feedback from Electrolux that every time we work with the recycled materials, we really realize that somehow we need also to change, let's say, the perspective. We need to change the way we design our components. We need to change the test we do on our components. We need a change in our minds, okay? Because a recycled material is not a virgin material, and that's the starting point. Starting from that, we need to understand what we can accept and what is not acceptable for us in terms of performance, in terms of aesthetics, and whatever it is. So sometimes, the working on a regular basis and, always doing the same thing, let me say, okay, when you change the materials, when you let's say, start using recycled materials, it's not enough. You need to change your mind. And that helps really in applying those materials. And again, I think that the collaboration, especially with the other companies like Urek, for instance, having different problems but with the same target, collaboration is key, always. So it's very, very important.
Thank you. Then, you like to react to Roland or no?
I can just agree. Collaboration is the key.
So, any reaction from Tom, or is it everything is said? Yeah, I think to finalize, this is the end of the Plast2bCleaned project, but it's not the end of the Plast2bCleaned process. It's the beginning. So we will continue with our work, and we will also continue with the idea and of making everything, all materials, really circular. So, and I hope the audience is also will contribute to that. If you are interested, I say it again, please let us know. And if you like to use our results or outcomes, also contact us, because we are willing to share. Mariana.
Well, I'm afraid we are coming to an end. There were no further questions on the chat for the panelists, but anyway, you can always, if you change your mind and you have a question, you can always redirect it to communication@sustainableinnovations.eu, the email you receive from your registration process, and we can readdress the questions to our panelists and speakers today. I want to thank everyone in the room for being present today, and also the ones connected online. It was truly a pleasure to have you on board. Obviously, we will continue our process, as Judith said, even if the project is over. But before we go, I would like you, because you didn't really have the opportunity as we did, the ones in the room, to know a bit closer what the process is. And for that, we prepare a very nice video. The video contains an interview to one of our speakers today, so that will ring a bell from your side if you were connected from the very beginning. And we will go further explaining what the process has been on the labs on Fraunhofer. And I will leave you now to the video. And with that, we close the webinar. As I said before, thank you very much for being with us today, and we will really hope to see you in the future. Thank you. I leave you now with the video.
I'm Sebastian Reinhardt. I'm a research scientist at Fraunhofer ICT, and I specialize in separation techniques and the recycling of aged plastics. Our goal in Plast2bCleaned is to develop a technically feasible and environmentally safe recycling process for plastics from WEEE wastes. And we've developed a plant within this project, which you can see behind me. We have successfully removed hazardous substances such as legacy bromine flame retardants from waste ABS and sent them over to our partner ICL, where it has been converted into harmless sodium bromide.
Alongside the chemical recycling, solvent-based recycling is one key technology to achieve the goals of a circular economy. This allows polymer to retain the structure and keep these in short material cycles. With the help of the interdisciplinary team from the Plast2bCleaned project, an efficient recycling process was developed and can be applied for a wide range of plastic polymers.